across them, and it causes it to black out. And you might think of linearly polarized light like this model here, but that's not a complete and proper interpretation. You see, linearly polarized light is actually two components that are perpendicular to each other. Now don't be confused. I don't mean one's magnetic and one's electric. I mean two electric field components perpendicular that on average add up to a polarized vector sum. Now, how do we know? Because if we put yet a third polarizer in between and rotate it 45 degrees, more light gets through. This means that all along it had a component in that direction. But what is circularly polarized light? To begin the experiment, you're going to need a pair of 3D glasses. Not this pair, hey, with the Beatles, with the red and green filters. And not this pair either. These ones are linearly polarizing. You're going to need a pair of circularly polarizing glasses. But how can you be sure you got the right ones? One trick is to look into a mirror with the glasses on and close one eye. If you do this, the open eye will be blacked out. This does not happen with linearly polarized glasses. My LCD computer screen is always going black when I turn this polarizer. It must be linearly polarized. But my iPhone, it never goes black. It must be circularly polarized. It does change colors slightly though. All polarizers have the effect of slowing down or diminishing light in one plane, but with circular polarizers there's an added layer that slows down only one of the planes by a fraction of the wavelength. The truth is, all transparent media slow down light to some degree. For example, in water, it's only 75% as fast as it is in air. And in glass, it's even slower. When it comes to a polarizing medium, the light travels at different speeds when it oscillates in different planes. But how do you get a substance to do this? The trick is, you stretch it. This slows down the light more in one direction than the other. You can also see the effect with a piece of packaging tape stretched between two polarizers. If you want light to become circularly polarized, you have to be very careful about how you slow the components down. Here again is the model of light that is linearly polarized. If it is going to become circularly polarized, then one of the components will get slowed down. Not too much. There. It is now late by 1/4 of a wavelength when it emerges from the circular polarizer. But it doesn't look much like a circle, does it? As the wave travels, the net vector sum traces out a circle. It is much easier to see this if we wrap a ribbon or a slinky around the model to represent the sum. Yeah, it looks a lot like a helix, doesn't it? So where is this well-engineered piece of plastic that turns a linear polarizer into a circular polarizer? It's right here. There. This little piece slows down the horizontal component by 1/4 wavelength, and this leftover piece is just a linear polarizer. Before you go, let's answer your original question about colors.